In this video, we're going to continue talking about aromatic compounds. In particular, we're going to be talking about ionic aromatic compounds and heterocyclic aromatic compounds. So ions can be aromatic if they contain an unhybridized p orbital that completes the continuous loop of pi electrons and also obeys Huckel's rule. So for instance, if we look at this cyclopentadienyl cation right here, we see that the pi bonds can form a continuous loop around it because all of the carbons are sp2 hybridized, but it only has the 4n electrons, which means that this would be anti-aromatic. And so we would expect this cyclopentadienyl cation to actually be anti-aromatic. Whereas if instead we have a lone pair here, rather than missing an electron like in this one, then we have the cyclopentadienyl anion right here. And now again we see we have the full loop of pi electrons, and we have the 4n plus 2 electrons in it. And so that actually makes this an aromatic compound. And one thing that's interesting about that is what happens is if we have this compound right here, that's not an aromatic compound. We can remove one of these hydrogens using this base right here, and it will turn it into this cyclopentadienyl anion right here, which is aromatic. And so it has that extra bit of stability. And so that actually makes this compound right here surprisingly acidic. So I wouldn't say that it's a strong acid, but it's a lot stronger than, say, just the cyclopentane, which would not have any of the double bonds, which has a pKa of 46, just because of that aromaticity in the conjugate base right here. And we can also see that with the cyclopentadienyl anion that the ring form is more stable than the linear version, and so that's another reason that we know that this is actually aromatic. Now, if we look at this for the version of this with the cation, so the cyclopentadienyl cation, now we see that this reaction does not actually occur, because once we protonate this alcohol on here, it's not going to want to leave, because that will make this anti-aromatic version of the ring right there. So the anti-aromatic version is going to be even more unstable, so it's going to be even less likely for that water to leave. And for this one, we see that the ring version is actually less stable than the linear version. So again, that's just another way that we know that this is aromatic. And given these considerations of aromaticity and anti-aromaticity, it seems like the resonance picture of these compounds will give a misleading suggestion of stability, where we see that the anionic version is actually going to be the more stable version since it's aromatic, where the cation version will be unstable because it is anti-aromatic. So even though they both have the same number of resonance structures, it is only one of them that is actually more stable because of that aromaticity. We can look at this for this 7 carbon ring right here, and now what we notice is that when we lose this alcohol right here, so that if that comes off as water, we get this tropylium ion right here, and this one is actually going to be 6 pi electrons, so it's 4n plus 2. So in this one, it's the positive charge version that is actually going to be more stable, whereas if we have the anion version like this over here, which has 8 pi electrons, this is actually going to be less stable. So this molecule up here is going to be more likely to form, and this one down here is going to be less likely to form. And again, we see that the ring version is more stable than the linear version. So again, that also shows us that it is aromatic. And so we again get a misleading view of what the stability would be if we just considered the resonance structures. These compounds both have the same number of resonance structures, but only one of them is stable and the other one is very unstable. And that is because of the aromaticity and anti-aromaticity respectively. Then we can also look at the heterocyclic aromatic compounds. So these are compounds that have things like nitrogens or oxygens or sulfurs in the place of one or more of the carbons. So if we look at this pyridine over here, this has a single nitrogen in this 6-member ring, and this will actually be aromatic. And we can see this because it has the sp2 hybridized nitrogen there. So it has that 1 p orbital, and it has 2, 4, 6 electrons in the pi system. So we have all of the sp2 hybridized orbitals, and we have these 6 electrons. So that is enough to make it aromatic with the pyridine right there. And what you'll also notice is that the pKb on here is relatively normal for an amine. That's because we have this sp2 hybrid orbital right here that has the lone pair that will readily bond with an H+ ion. That's because we have the sp2 hybridized orbitals, which gives us that p orbital right there. We also have 2, 4, and then 6 electrons in our ring right there. So those electrons can all be part of that pi system. But what we notice here is that now the pKb is quite a bit higher. So this is a much weaker base. And the reason for that is because if we put an H+ onto that lone pair there, that makes it so the lone pair can no longer be part of that pi system. So it turns the nitrogen into an sp3 hybridized nitrogen. And so that takes it out of our pi system. And so that means that this pyrrole right here, the aromatic version, is going to be favored, and so that's why it is a weaker base. We can also have more than one nitrogen atom, so we could have something like this pyrimidine or this imidazole right here. And what we notice for these is that most of the non-basic, so the pyrrole-like nitrogens, so remember this was our pyrrole right here, have 3 single bonds and a lone pair in a p orbital. And so that would be like this one right here. So we see it has the 3 single bonds, it has no double bonds going to it in our structure, and so that is non-basic. Where most of the basic, which are the pyridine-like, the nitrogens have a double bond in the ring, and their lone pair is in an sp2 hybridized orbital. So we see this one right here, this one right here, and this one right here all show a double bond to some carbon in the ring in our structure there. And those are all the basic versions, meaning that that lone pair that's shown on it is actually ready to pick up an H+. And we can have other heteroatoms in here besides just nitrogen. So we saw it for the carbon, which was the anion right there. So we can have the ionic versions, we can have the nitrogen, but we can also have things like oxygen and sulfur, which can both bring one of their lone pairs to bear in that pi system. So we see down here, this oxygen has one of the lone pairs as part of the pi system, and the other one as the sp2 orbital. Similarly for the sulfur, one of these is part of the pi system, and the other lone pair is the sp2 hybridized orbital right there. Another thing to note is that we can have these carbonyls be part of our aromatic system. So this molecule right here would actually be considered aromatic, and we can see this if we think about it in terms of the resonance structure. So if I take these electrons down here, put them right there, put those ones up over there, we now see that we have just made our quintessential aromatic ring right there. And this we already looked at in the previous video, but now it should hopefully make even more sense after what we've talked about in this one so far. We can have these ionic versions right here that are aromatic or anti-aromatic. We can have them right here that are aromatic. We can also have our heterocyclic compounds right there and right there. And again, we see Huckel's rule says that if it has 4n plus 2 electrons in the pi system, then it's aromatic. If it's just 4n, then it's anti-aromatic. One last thing to talk about in this video is that there can actually be multiple of these rings fused together to make these larger aromatic structures. The book calls these polynuclear aromatic hydrocarbons, or what I learned it to be was polycyclic aromatic hydrocarbons. So if I use those interchangeably, sorry, but the book has it one way, I learned it the other way, so I will usually probably call it just the polycyclic aromatic hydrocarbons. But anyway, these are a couple of instances of this. So we can have the anthracene right here, which is just 3 benzene rings put in a linear fashion like this, or we can have the phenanthrene right here, which is just going to be 3 of these benzene rings but with kind of a curve to it like that. And these tend to get more reactive the larger they get, behaving more like non-aromatic systems. So we can actually do these regular addition reactions, so putting the bromine onto it right here and here, and similarly with this one, putting the bromines onto it right there. A few interesting cases of this is when we have something like graphite, which is just a lot of these put together, so it can be extremely large, so it can be billions or more atoms of these polycyclic aromatic hydrocarbons. And interestingly about the graphite is that they are electrically conductive in the direction parallel to the plane. So we could have electron conductivity going through it like that, but not when it's perpendicular. So there would not be any current going through it that way. And there are a few other examples here, so we can have things like the buckyball or the carbon nanotube. Another important place is when we have these in the biological setting. So in biology, we get a lot of these fused heterocyclic rings like this. So things like purines, which show up in DNA, indole, which shows up in amino acids like this tryptophan here, and we can also have things like the benzimidazole, the quinoline, the benzofuran, and the benzothiophene right here. And down here we can see just a few examples of where these show up in some drug and other biological settings. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.